Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, which means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, all of the cool stuff happening inside the universe. I love being a cosmologist and I love chatting to people about all of the cool things I get to study and get to work on. So welcome to everybody who's a return viewer. Welcome to first-time viewers. Great to have everybody here. Hey, David, Ben, Paul, great to see you in the comments, as always. Always great to see people here. David Howden, great to see you as well. Nice to see all the regulars coming back, and welcome to anybody who's new. For anyone who doesn't know what this show is, this is the place where you get to ask anything you want about cosmology, about space, about academia, about life in general, and I will do my best to try to answer. Now, of course, I don't have all of the answers. It will often be the case that I will not know how to answer your questions, but I'm going to do my best. As always, there are no stupid questions. We're all here to be curious, be kind, and learn things together, so you can ask me anything you want. Hey, James from Barcelona, great to see you. Yeah, if you want a flight, that is a very valid reason to miss my stream. And also, I don't expect people to tune in every week. It's great to see you all coming back, but really, you don't need to apologize for missing me one week. That's always fine. I'm still surprised that so many of you come back after so many years watching me. I know there are people who have been watching for over 7 years now, so it's great to see that you're all still here after so long that you haven't got bored of me yet. So welcome back to anybody who's a return viewer. Welcome to new viewers. Great to have everybody here. More comments. Last week was busy, so we didn't the trip to Spain and beyond. You didn't hear about my trip to Spain and beyond. Indeed, you didn't. So a couple of weeks ago, time is weird. At some point in February, almost a month ago by now, I flew to Spain for a week, got to spend a week with my family, which was really nice. The disadvantage of living in Finland is it means I'm far away from family, so it was really nice to see family again. And then I went from Spain, caught a flight up to Germany, spent a week with my partner, and then did an amazing trip back from Germany to Helsinki using trains and boats. It was a 3-day trip, and I did it carrying my telescope. I just realized I'm hyper today. There is a reason for that. So yeah, I took my telescope from Cologne in Germany to Helsinki via trains and boats. It was a completely exhausting 3 days. I barely slept, but it was an amazing adventure. I met lots of people. I chatted to lots of people. I got to see some of Stockholm. I got some amazing views from the trains and from the boat. It was amazing, and now I have my telescope back with me in Helsinki, which is amazing. So thank you for asking, David. Trip was really fun in some way. Spain, Germany, and then up through Europe with telescope. Great trip. Okay, before I get into more questions and comments and tangents, please, if you haven't done so already, please do subscribe to the YouTube channel, leave a comment, like the video, all of the usual stuff. It really does help boost engagements. So I appreciate you doing all of the usual YouTube things. And if anybody wants to financially support Cup of Cosmology, that is always very much appreciated. And always, I very much appreciate anyone who does that. There's a link in the video on screen here down below and in the video description. I'm on Ko-fi. You can buy me a cup of coffee. All the money that I get there just helps with running the show and keeping the webpage and everything like that. But all Cup of Cosmology content will always be free, so please don't feel ever any pressure to donate. It's always an option, but never a requirement. Okay. Some people are already pointing out here that last week we went the entire stream without seeing the CMB graphic. And that is correct. Last week we were doing quirks and creativity in general relativity. And there was one chance where I almost brought up the CMB, but there wasn't a real chance to slip it in conversation. But we always do get the CMB anyway, because it is in the Cup of Cosmology logo, which is up on the screen. You know, every stream starts with my loading screen, which is this, which means every stream starts with the CMB. So even if I don't manually put it on screen, you will always get the CMB. But never fear, the CMB is never far away. So even if we didn't see it last week, we can absolutely compensate by bringing it up this week. Less than 6 minutes today because people mentioned it. CMB, cosmic microwave background radiation, my favorite thing in the universe, tied with gravitational waves, my favorite thing in the universe. Always happy to talk about CMB. Okay, that was a long ramble there. That doesn't count. The logo absolutely does count. I added the CMB to the logo, or I requested the CMB in the logo specifically so it would be the first thing you see every time I start the show. It is there by design so that it's there every single week, but now you got the real one. And on the topic of CMB, I have finally put my CMB poster up in my office. So even when I'm working on gravitational waves, I now actually have 3 CMBs around me in the office. So there's always plenty of CMBs wherever I am. Someday, maybe we'll have a similar background map for gravitational waves, and that would be absolutely amazing, and that will go up next to the CMB on my wall. Okay, I see there's actually a couple of comments, but I want to answer the questions that are related to what I've been saying. So an astronomical telescope, yes, when I was saying that I brought up my telescope, it is indeed an astronomical telescope. I am an amateur astronomer. I love looking through my telescope. I love pointing out cool stuff through my telescope to other people. I have a Celestial and Astral Master reflector telescope. It's a very nice one for beginners. I've had it for about 10 years and done some amazing observations with it. And now the telescope is here in Helsinki, which means I can actually use it again. Because having a telescope that is several countries away is not very helpful. I am always hyper, but am I extra hyper? Yes. So been having a good weekend, made some amazing food. I went out to the forest today. It was really fun. I spoke to some random people, always nice. But about 20 minutes before starting the stream, I went down a loop of nostalgia, early 2000s pop music with some very, very bad, questionable music. And at some point, like 5 minutes before starting this stream, I was listening to Barbie Girl. From there, jumped into Asada here. So I have like really bad pop music playing in my head, which means I'm more hyper than usual because I'm mentally still dancing to the pop music. Music is always a good way to get me hyper. Okay, see a comment here that people still upset that we missed the CMB last week. Yeah, we did. We did miss the CMB last week. I know there have already been some physics questions. I will get to those as well. If Helsinki is in Eastern European time zone, why do you use Central European time zone? Great question, James. The reason being that a lot of people don't actually realize that Helsinki is 1 hour ahead of the rest of Europe. So when I make plans with former collaborators who are in mainland Europe, I always put things in their time zone because occasionally I've made comments like, okay, so that's 1 hour later for me, and people are surprised. A lot of people don't realize just how far east and how far north Helsinki is. So because most people don't realize that Helsinki is in a different European time zone to the rest of Europe, I just default when using Central European time, because if I start saying, Helsinki time, then a lot of people are going to be like, wait, what time zone is that? Which is why I always express things in Helsinki time and in East Coast, and occasionally I'll say the time in West Coast as well. I know a lot of you in the US change your clocks today, so the stream is an hour later for you. We change in 2 weeks, so then it will go back to normal schedule. 130 millimeter or so telescope, exactly. Yes, it is 130 millimeters. That is the size. Okay, when are the Cup of Cosmology coffee mugs on sale? I need to make Cup of Cosmology coffee mugs. Yes, that is something that has been on the wish list for a long time. I know some people are interested in it. We could get a mug with the logo and Cup of Cosmology hashtag. It would be great marketing. Have to look into it, have to see if it's actually viable, have to see if enough of you would buy it to justify actually making this. If so, I will talk to the person who designed all of my amazing logos and banners and see if we can do something about making a mug. Whew, okay. So are you saying the cosmic microwave background is always in your background? Aha, I love it. Yes, it is. Yes, absolutely. Okay, so someone's putting lyrics to a pop song with cosmology. She's a cosmology girl in a cosmology world. Yes. If anyone writes pop lyrics or any type of lyrics about cosmology or physics, I will absolutely love that. And there's a high chance I will try to sing along. So if anyone wants to make any physics themed or Cup of Cosmology specific lyrics, I will love that. Yes. Is Helsinki north of the Arctic Circle? No, it's not, but the Arctic Circle is north of Finland, so you can actually go up there in Finland. And I was very close. No, I did cross the Arctic Circle line when I went to Lapland some months ago. And Finland is part of Eastern Hemisphere, not Western. Yes, that is the thing. Mugs are not cups. Yeah, well, mugs, cups, same difference, right? Most of Europe is in the Eastern Hemisphere. Yeah. the world is weird, and we always do this weird projection of centering Europe at the center and then messing up the size distribution of everything. This map that I have behind me is actually slightly more accurate in terms of the size of continent because it uses a double bubble system instead of one. And that is a complete tangent, but there are a lot of different, okay, so hyperfixation time. There's a lot of different projections you can use for maps, and they're all really interesting because it comes down to the question of how do you project a sphere onto a two-dimensional surface. And this is basically a holography question, right? You're trying to contain all of the information of a three-dimensional thing in its two-dimensional image. So you are going to lose information. And you can't talk about maps with me. I will absolutely hyperfixate. I love maps, and it's really curious to see how you always distribute, how you put a map on paper. And it's not just when mapping the globe that we have this issue. We also have this issue when doing things like mapping the CMB, because the CMB is actually a sphere around us. We're at the center of this sphere around us. So it's equivalent to trying to map a globe. And this is the projection that people have chosen, the hammerhead projection. But you could equally use the CMB as kind of the flat one that we're used to when projecting the Earth, or even the one with double spheres like I have behind me. So all 2D projections of a 3D object will lose some information, but we have to make the best we can of trying to put the information in a more manageable way. Peter's projection is an equal area projection, as is a Hammer-Atoff, like that CMB map. Exactly. Just gives me another excuse to talk about CMB. Also, if anyone finds any obscure maps, send them my way. I love obscure maps, like maps of the heights of buildings. Love it. I follow several different accounts on different social media that is just about maps, and it's so fun. Local time and UTC time is best in my opinion. UTC is less complicated to convert to local time, where the time zone is half hour out and we have no daylight saving time. Yes. Yeah, time zones are weird. Being aware of where everyone lives is weird. And daylight saving time is nonsense. We should stop changing our clocks. There is no reason to do this. There is no scientific benefit to changing our clocks twice a year, and there are a lot of downsides. This is a hill I will die on. Daylight saving time is a bad idea, and we need to stop doing it. The sooner the better, and we need to stick to actually winter time. Sticking to summertime is not a good choice, but it's better than changing every 6 months. You bought a map centered on your house. That is really, really, really cool. Love that. There's actually a web page that you put a city in, and it draws the city as if it was an old classical map, just like with drawn lines. And it draws all the roads in your city, and you get this like vintage drawing of any city. It's so cool. And yes, the terrible maps page is very funny. There's some very funny maps there. Most people picture Europe in their head with UK and France as centre, but East is huge. Yes, agreed. Stop daylight saving time petition. I will sign it. Every single year I go on a rant about this. We haven't even entered daylight saving time in Europe yet, and I am already ranting about it because daylight saving time makes no sense. Absolutely should stop doing it, and it messes up my sleep rhythm. I already have issues sleeping, and daylight saving time comes along, and suddenly my sleep's messed up for a week, and then I get used to it, and 6 months later it's messed up again. Hate it. Okay, we're 15 minutes in. We've barely done any physics, lots of rambling, lots of tangents, but someone mentioned maps, you mentioned the CMB, easy topics to get me distracted. Also, the CMB is literally a map of the early universe. How could I not love it? Yes. Anyway, let's see, going back through the comments, I know there were some actual physics questions beforehand. So let me just go and make sure. Oh, I missed a comment there. I had a mate in the UK who has a telescope in Chile and one in Spain, which he operates remotely. Yes, operating telescopes remotely is great fun. Incidentally, if you want to operate a telescope remotely, the iTelescope network is a great place for that. iTelescope is a great network. Lots of cool telescopes you can sync up to remotely. And they also do a lot of cool outreach talks every Friday. I've given 3 talks for the iTelescope network now. And this coming Friday, they have someone who's been on Cosmology giving the iTelescope talk. So if you want to operate telescopes remotely, check out the iTelescope network. I'm never paid to do these like mentions and ads. I just like slipping in references to other accounts that I like and other things that I like. So, I'm just making it clear I'm not paid to do these ads. I just like promoting cool things like CRISPR's Act. Okay, going back to the actual questions. I know it was quite far away. Two questions. We have a question from David Howden, left over from last week, and a question by Paul Hess. Question by Paul: what do the large early universe galaxies mean for our models of cosmology? And I like this question, and the answer is I'm not ready to answer this question yet. So there's some really cool, yes, Christian Sasser uses these remote telescopes at the iTelescope network. It is a great thing to do, absolutely. Hey, Suleep, hi from Germany. Hi from Finland. Nice to have somebody from Germany here. I lived in Germany for many years, still have a lot of emotional attachment to Germany. So always nice to see people in Germany here. Okay, so the JWST, the Just Wonderful Space Telescope, keeps finding galaxies that appear to be a bit older than our standard model of cosmology expects. And this is very intriguing because we can't quite explain it yet. Now, it's still at the stage where the JWST has seen some old galaxies, but not too many. So it's still kind of in that region of, should we be concerned about this? Is this something to look into further? And we're not yet sure if this is a big problem, a minor problem, something in the JWST data. And it's also something that I haven't yet read up enough about to be able to answer that confidently. I have a bunch of things bookmarked of people saying like, oh, this is a problem, and other people saying this is not a problem. So that's something that I absolutely want to read up about a bit more before I answer it here. But it is very interesting that we are finding galaxies that are a bit older than our standard model of cosmology predicts. It just means it's exciting. Anytime we find something that's an anomaly or different to what we expect, it's exciting. But at some point, I do want to go more in depth about what this actually means. And let me just get the question properly again. It's quite far back by now, so where was the question? So what do the large early universe galaxies mean for models of cosmology? We're figuring it out. I realize that my answer might not even be the answer to your question. So we're also finding galaxies in the early universe that are bigger than we expected, again with JWST, and this is also a problem. But for now, I would leave it as it's a curiosity, but it's not a crisis, it's not a problem. It's just something that's intriguing and interesting. But we're definitely not baffled by this. Don't believe the thing of scientists baffled. Okay, then there was a question by David Howden, question left over from last week. How can there be a charged black hole? Wouldn't something photons have to get out to carry the charge? Yes. So that was a question that we had problems answering last week as well. So and black holes usually have, before I get to the black hole question, when will we know if JWST has redefined the universe? I think we need more data, right? It's always the thing that it's still in its infancy. There was just another big round of proposals submitted for the JWST for new places it can look, new science experiments, new things to do with it. I think some of those will really push this question of the galaxies. So I think over the next few years, we're going to get a huge amount of data from JWST, and it's going to tell us a lot about early universe galaxies. So has it redefined the universe? Not just yet, but stay tuned. I think within the next year, maybe 2 years, there's going to be a lot more coming in this regard. Charged black holes. So we said last week that black holes can have spin, they can have mass. Now the most important, I was just asking Google, do black holes have charge? And I realized I can no longer type and answer questions at the same time. So the most important property of a black hole is going to be its mass. Its mass gives you the overall radius as well. So you can have a black hole with a specific mass and a specific radius. The second important property about a black hole is whether it has spin or not. So just so we're all on the same page, a black hole is a region of space-time that is so dense and nothing can escape, not even light. Most black holes are formed when a star collapses, reaches the end of its lifetime and collapses. You can also have you can also have black holes formed in the very early universe, hypothetically, and you can have supermassive black holes. We're not quite sure how those are formed just yet. But my computer's just frozen on me. This is very irritating when it does that. Okay, back now. Hey, Scott, great to see you. Stupid time change, agree. I've already ranted about daylight saving time, but great to have you here. How far ahead do scientists book time for Hubble and JWST experiments, observations? About a year in advance, I think, is reasonable. So about 2 months ago, there was a deadline for the new applications. And I think it will be announced which ones are selected in a couple of months, and then they queue them up and when there's good time, and they try to do them together. Like, if they need specific regions of the sky, maybe you can do them together. But I'm not involved in any of these direct observations, but I would imagine about a year in advance is kind of the timeline we are looking for here. Okay, so black holes have mass. Second thing black holes can have is potentially spin. This is angular momentum. Now, even though it is a lot easier to describe black holes that don't spin, it's just the mass is nicer. This is what is known as a Schwarzschild black hole. It is much more realistic that black holes should be spinning. In fact, every observation, every direct evidence we have for black holes show that they are spinning. And the photos we took of the supermassive black holes at the center of our galaxy and M87 are also spinning. This means they occur black holes instead of Schwarzschild black holes, which makes them mathematically extremely difficult to describe. So we know that black holes have mass. We're pretty sure black holes have spin, even though it would be a lot nicer if black holes didn't have spin. And then last week we mentioned about, can black holes have charge? Now, there is it's a difficult question, and one that you can theoretically have charged black holes. The way this might happen is if a lot of charged matter falls into them, then the black holes themselves might acquire charge. Now, as you can see, this is something that I'm not confident in my answer. So theoretically, yes, you can have charged black holes because they can accrete matter, and if they accrete a lot of things that have charge, they themselves can also have charge. But there is a limit to how much charge they can have, and it's something that I absolutely do not know enough about to answer confidently. So you can have a charge of a black hole, but usually we neglect this. In the same way that we neglect the spin, we do often neglect or ignore the charge of black holes. But there can be processes that lead to a small non-zero charge. So these are both classical and quantum processes, and that's what I just found on the 2-second Google search there. So you can see that this is something that I'm not confident on. So to recap, mass important, spin important, but we neglect it. Charge of black holes can be possible. There are different processes that can give charge to black holes, but I don't exactly know which processes these are, other than accreting matter that has charge. But black holes cannot acquire too much charge. There is a theoretical limit that you can calculate. And then this charge probably doesn't stay, it can dissipate. So for simplicity, let's assume that black holes are not charged because it makes the conversations easier. But yes, it's a leftover question from last week, and I'm going to leave it slightly as an open question again because it is a complicated one to answer. We tried to answer it last week and got slightly lost in the answer as well. Okay, so let's catch up with comments again. Yes, just hello, welcome to everybody. How long in advance do we ask for stuff with telescopes? Quite far. Okay, so I think those were the earlier questions that I hopefully answered now. Question from David Dunn here. Are you familiar with cuboles as a possible dark matter component? There are a lot of possible dark matter components. I'm not exactly sure what the cuboles are. There are balls of quark matter, if that's what you mean, but I'm not completely sure what you mean here by cuboles. But there are a lot of different types of dark matter. There's a lot of different proposed types of dark matter. Of course, we actually haven't found any dark matter yet, so we have no idea what dark matter is. I mean, it's probably not space dragons, but otherwise there's a lot of things dark matter can be. Everything from primordial black holes, so black holes in the early universe, to a swarm of particles. It could be axions, it could be a lot of things. I've heard ideas of dark quark nuggets, so little nuggets of dark matter. Instead of having like particles, you have little chunks, kind of like chicken nuggets, but in the dark sector. Probably about as mysterious in the ingredient list. So you can have these quarks that are made like little nuggets of quark dark matter. There's a lot of random candidates for dark matter. Unfortunately, until we actually find something, all of this is just a long list of models. And what we usually do is we rule out dark matter candidates. For an example, you can say if dark matter interacts with something or bumps into stuff in the early universe, it would mess up the CMB, cosmic microwave background radiation. So you can use that to say, okay, well, dark matter probably doesn't do this, dark matter probably doesn't do that. But until we actually directly find dark matter, It's always going to be many, many more candidates. Finding dark matter, of course, is very difficult because dark matter cannot be seen. Tea is still too hot to drink. As people on this show know, I have issues with when is the best time to drink tea. So just to recap here, dark matter is this weird type of matter that accounts for 80% of the matter part of the universe. So the universe has three main components: everything you see, everything you're accustomed to, everything from me to my table to my very hot tea. This is normal matter. Normal matter only accounts for 5% of the energy budget of the observable universe. Then we have another 25% that is in the form of dark matter. Dark matter is this weird type of matter that interacts via the gravitational force but doesn't interact via the electromagnetic force, which means it does not emit light, it does not absorb light, it does not reflect light. As far as light is concerned, dark matter is not there, which means it's invisible and very, very, very difficult to see. Obviously, you can't see it. If it's invisible, it's very difficult to study. The remaining third component, the remaining 69% of the energy budget of the observable universe, is in the form of dark energy. Dark energy is this mysterious type of energy that is driving the accelerated expansion of the universe, is pushing everything away from everything else, and that's pretty much everything we know about dark energy. Negative pressure, cool thing to talk about. So dark matter, we don't know what it is, but we're pretty sure it's there. If we didn't have dark matter, the CMB wouldn't look the way it does. In order to get all of the orange and blue dots here, you need something that behaves very much like dark matter. Also, the way galaxies look, there's a lot of different things that can tell us about dark matter. So the question was, am I familiar with cupules? The answer was, here's the dark matter explanation. So no, we're not completely sure what dark matter is. We're not actually very sure what dark matter is. Cupules are one of the many possibilities there. Okay, I know there were some cool questions there that I wanted to get to. There is still a question about primordial black holes that I'm aware of that I want to come back to, but while we're on dark matter, let's stick with dark matter. The Axions were in Doctor Who, I think, probably. You know, Doctor Who pulls out random names like the Sycorax and Praxicoricophalopatorius, so, you know, maybe they used Axions at some point, would not surprise me. Do not research the manufacturing process of chicken nuggets. Actually, I think you should. You know, we all should be more aware of what we're eating. And I think if people knew how chicken nuggets are made, you would not eat chicken nuggets. This is the vegetarian in me coming out here. So yeah, absolutely do look up how chicken nuggets are made. I encourage you to do so, unless you actually really love your chicken nuggets and want to remain oblivious, because nasty. I wonder if dark matter can be responsible for pulling together the early universe large galaxies. It could be. It very much could be. So there's a question, a lot of questions actually. There's one of the many open questions in the field is what came first, supermassive black holes or galaxies? So we know that we're pretty sure that at the center of every galaxy, there is a supermassive black hole. Supermassive black holes kind of hold these galaxies together. We're not sure what came first, but dark matter could help address this question. In general, we know that dark matter set the scaffolding upon which galaxies could form. Does it help us answer what came first, black holes or galaxies, supermassive black holes, galaxies? Maybe, depending on how dark matter behaves, but based on what we've seen, it doesn't help us much. Now, the question that Paul is asking here is, can dark matter be responsible for causing these slightly bigger than expected galaxies in the early universe? So I'm thinking about this question because we're very sure, so a lot of what we know about dark matter today comes from how galaxies look and the evolution of galaxies over the history of the universe, so how galaxies have changed. And this tells us a lot about dark matter in the early days and dark matter today. And of course, we have the cosmic microwave background radiation, which sets an anchor for what dark matter looked like at this time here. Now, the cosmic microwave background radiation was formed about 380,000 years after the end of inflation. And if I go to this picture here, you can see 380,000 years after the end of inflation, we formed the CMB, the cosmic microwave background radiation. Galaxies, however, are formed quite later, which means by the time galaxies are formed, we already have one of the bookends about dark matter. We have the CMB. So in our current picture of what dark matter does, which is based on what we've measured from the CMB and what we measure today, these galaxies should not be as big as they are, and this takes into account the effects of dark matter. So now, if let's say that JWST is correct and these galaxies that it's found are bigger than what they're supposed to be, the question Paul is asking here is, can we blame dark matter for this, so to speak? However, this would mean that dark matter, something's gone wrong because with our understanding, because based on what we've measured at CMB times, we include dark matter from the CMB moving forward, and then we get galaxies that aren't as big as the ones that potentially have been found. So can dark matter be responsible for pulling these together? Not within the standard cosmological model. Now, of course, you can do other things to dark matter. Maybe you can make dark matter talk to itself. Maybe this would help galaxy formation. I'm sure there are a lot of people asking that question. I have not yet seen any papers linking these two things together, but I'm sure people will come up with ways to tie together these very big galaxies with random dark matter models, because this is always cool to do. And if it turns out that there really are bigger galaxies, it questions our standard model of cosmology, which includes questioning the nature of dark matter. Okay, dark energy is 69% of the universe. Nice. Yeah, it would be nicer if it was like 69.42, but yes. What would you say is the, okay, some more quick comments here. I didn't eat chicken nuggets for a long time after learning, but hunger won out in the end. Okay, right. So there's a question here by Pref about how accurate are these percentages, and I really like this question. So this is this thing here. We have these percentages. 68.9% of the energy budget of the universe is in the form of dark energy, 4.9% normal matter, 26.2% dark matter. The question is, how accurate are these percentages, and how can you be so sure they're accurate? Now you see here I have the 0.9, the 0.2, the 0.9 again. This is the percent level precision that we have, or the sub-percent level precision that we have. And to answer the question of how do we know this, I need to go to my favorite image, the cosmic microwave background radiation. This is a snapshot of what the universe looked like 380,000 years after the Big Bang. At this point in time, you have dark matter doing its own thing. You have protons, you have electrons, and you have photons, which are particles of light. The three of these are constantly bumping into each other. As the universe cools down, protons and electrons combine together to form neutral hydrogen. At this point, the photons can no longer interact, so they break away and start traveling freely throughout the universe. I just said neutral hydrogen. Yes, they form together, they bond together to form hydrogen. The photons, particles of light, break away and start traveling freely throughout the universe. They've been traveling pretty freely since then, and when they reach us today, they've been redshifted into the microwave range of the electromagnetic spectrum, and they give us a CMB. And by studying the statistical properties of this, like how many hot photons and how many cold photons we have, we learn about the state of the universe at the time these photons broke away. And if you change the amount of dark matter or dark energy or normal matter by a tiny amount, this picture would look very different. So if you change the amount of dark matter, you would get bigger clumps of a specific scale. If you change the amount of dark energy, everything looks different. So when we say there's 26.2% dark matter in the universe, it means that we've tried 26.1, we've tried 26.3, and neither of those fit the CMB as nicely as 26.2. In fact, this is a very pretty picture, but this is not how we do the science. From here, we take the fingerprints of this, and what we end up with is this plot here. On the vertical scale, you have the amount of blobs of a specific color that you have with the temperature fluctuations. On the horizontal axis, you have the size of these blobs, orange and blue blobs. You can see here in red the data points. The red dots correspond to what we've taken from here. The green line is our best attempt to reproduce these red dots. This green line that you see here has 26.2% dark matter, 68.9% dark energy, 4.9% normal matter. If you change any one of these numbers very slightly, this green line no longer goes through the red dots as accurately. So to the question of how accurate are these percentages, very accurate actually, incredibly accurate. It is one of the most precise measurements we've ever been able to do in cosmology, or the most precise. How sure are we? We're very sure. Why? Because the CMB told us so. Okay, and you gave me a chance to talk about CMB again, so thank you for that. More questions? Let me just, I can call you a Pratt. I'd rather not, but okay, I can call you Pratt. Perfect, I'll call you Pratt. Sorry for the bad joke I just made there. Just caught up on comments. Yeah, I'm still catching up on comments. I think the amount of dark energy percent is increasing over time. Is the ratio between normal matter and dark matter staying the same over time? So the overall amount of dark energy and dark matter, so these percentages are not changing. What is changing is their density throughout the universe. So when we're talking here about percentages, we've normalized everything. So you take the total amount and you normalize it with respect to that, and that is going to stay the same. What is changing is their density because the universe is expanding, and the way these species dilute throughout the universe is different. Dark energy is constant everywhere. Dark matter is centered in galaxies. This changes their behavior in an expanding universe, but these percentages are fixed. They're not going to change. What is changing is the density of the species. But what I'm showing here is the kind of the absolute density normalized to something that is also growing with the expansion of the universe. But the ratio between normal matter and dark matter is actually what gives you the height of the first peak here. So this first peak here in green, you wouldn't have without the right ratio of dark matter to normal matter. Okay, yes, Fourier transform, absolutely. Okay, so there's a few questions. There's at least 3 questions I still need to answer. I know there was a primordial black hole question that's noted. But we're on the topic of dark matter. Is it possible for virtual particles to be dark matter candidates? So a virtual particle is a particle that doesn't actually exist for a long time, but it exists virtually, which makes no sense. But you can imagine you have 2 particles that come together, they smack into each other, and then they go away again. What is actually happening here is you have usually some interaction. So for an example, if you have 2 electrons coming together, they bump into each other and then they go away. What is actually happening here is they exchange a particle. And this particle is a photon. It's like one of them is going to emit a photon, the other is going to absorb a photon. This is how the electric charge works. But this photon doesn't really exist anywhere. It's just something that allows this interaction to take place. Particles come together, photon is created, it's absorbed immediately, particles go away. What goes in and what comes out is the same, but in order for this process to happen, a virtual particle was used. A virtual particle appeared and then was given back, so the overall energy is conserved. Could these virtual particles be part of dark matter? It's an interesting question, and the problem here is that we know that the effects of dark matter take place on large scales across the whole universe. Virtual particles are generally, by definition, very short-lived. So it would be quite hard to have virtual particles be able to account for the properties we see of dark matter, just because these virtual particles don't really hang around long enough to, for an example, affect the CMB or to affect the overall structure of galaxies. So there might be ideas of using virtual particles to try to explain dark matter, but I'm not completely sure how that would work because they are very short-lived. I like to think of dark energy as empty space. The bigger the space, the faster it expands, like a feedback loop leading to runaway expansion. That is a very interesting way of phrasing it, and I'm going to put a pin on that because there is actually a topic I want to talk about at some point today. And despite the fact that it might seem like I'm rambling a lot today, there is a goal, and I have mentioned several key pieces of information that I'm going to bring together at some point later on in the stream. So dark energy, keep a pin in these conversations. And there are still 2 questions that I missed. Let me scroll back to find the primordial black hole question. It's in here somewhere. Okay, question from Ben. And it was 17 minutes past, so quite a while ago by now. If it is only possible to detect non-feeding primordial black hole by observing its effect on space-time, are we sure we know how many there are? Absolutely not. Primordial black holes is a very contentious topic. So usually when we're thinking about black holes, we think of a star that's reached the end of its lifetime, it's collapsed, huge gravitational presence, huge gravity field here. This leads to a black hole. However, in the very early universe, you can already have regions of space-time that are really, really dense and directly collapse to form black holes. This is what is called a primordial black hole. Now, these are hypothetical. We are not sure primordial black holes exist. We are not sure if there are any, if they existed and they've dissipated by now. But depending on how you form primordial black holes, they would fall in the exact mass range of the ones that LIGO and Virgo have found. So, and primordial black holes could account for some or all of the dark matter, depending on who you ask. But primordial black holes, as all black holes, are very, very difficult to observe. The only thing that really sets primordial black holes apart from stellar mass black holes is the mass range. But you can change the mass of your primordial black hole by changing the way it's produced. So then if you could ever look at a black hole, you wouldn't be able to directly say this came from a star or this is a primordial black hole, because their behavior is the same. It's just the way they were formed that was different. So we don't know how many primordial black holes there are, if any. But there are some cool things you can do. That, one of the most well-known candidates for dark matter is what is known as a weakly interacting massive particle, which is a particle that, as the name implies, has mass and interacts very weakly. And this is what a lot of detection experiments are searching for. However, we have not found weakly interacting massive particles yet. There's always caveats, there's always ways you can change the theory to explain why we haven't found them yet, but we haven't found them yet despite a lot of experimental search. But weakly interacting massive particles are mathematically convenient. Of dark matter particles, they're one of the easiest to motivate. And one cool thing is that there's a lot of models of these productions of primordial black holes that mean that primordial black holes and WIMPs cannot coexist. So there's some papers stating that if you find just one primordial black hole, you rule out the standard WIMP scenario, weakly interacting massive particle. Of course, then you can find caveats to this, but technically, if you take this at face value, WIMPs and primordial black holes do not coexist. And measuring just one primordial black hole is enough to rule out a lot of WIMP scenarios, which is really cool when you think about it. Therefore, if we can ever directly say that there is a primordial black hole, it would be amazing, because for one, it would tell us that primordial black holes exist. And for two, it does bring into question our standard dark matter paradigm, or one of the most well sought after candidates for dark matter. So that's fun. But we haven't yet found any primordial black holes. Are primordial black holes like really small, like microscopic? Again, depends how you form them. So the size of a black hole is going to depend on its mass, assuming it's not rotating, which, good approximation, we pretend. And you can change the mass of primordial black holes, but it is usually going to be less than the mass of a stellar mass black hole. Now, the cool thing is, some of the ones found by LIGO and Virgo are in the smaller end of the mass range, kind of like around 20 solar masses, where you're more likely to find primordial black holes than stellar mass black holes. So primordial black holes are considerably smaller than normal black holes. They could be very, 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 very small, but still very, very, very massive. Smallest stellar mass black holes about the size of Paris. That sounds believable. Primordial black holes would be even smaller, but if you had enough of them, they are still very massive, and even if they're not big, they could actually do a lot in terms of explaining dark matter. However, not everyone is convinced. There was a period where every week there was a new paper like primordial black holes are dark matter, and the next week primordial black holes are ruled out as dark matter. You can still find hundreds of papers with this back and forth. There are some people who are convinced that primordial black holes are the answer. There are some people who are very much not convinced that primordial black holes will ever be found. Tea is currently at optimum temperature 48 minutes after I made it. Taking data so that I know when to drink it. You didn't know that the universe wasn't big enough for primordial black holes and WIMPs. Yeah, it's really cool. It's not so much that it's not big enough, the universe is big, and I know you're using a figure of speech there. It's just that by the way that they're produced, you cannot produce both in the standard scenario. There are caveats and ways around it. But yeah, WIMPs run away from flights with primordial black holes. And then you get the other dark matter candidate known as MACHOs, massively compact halo objects, which is probably not, it's not, well, it's something that is another dark matter candidate, where instead of tiny particles, you have massive compact objects. And they're called machos just to make the joke with WIMPs. So we have WIMPs and machos. And yeah, physicists, we cannot be trusted to name things. We really should not be trusted to name things, like, ever. We either give things names like WIMPs and machos, or we give things like names like the Very Large Telescope. And I wish I was kidding, but the Very Large Telescope is actually a thing, as is the Extremely Large Telescope. These are actual names that we've given things. Physicists, do not trust us in general. Okay, so I answered the primordial black holes being really small. Question from James, when we were talking about virtual particles, are those elements discovered by colliders which go away almost immediately considered virtual? Not necessarily. There can be other things that are short-lived, other particles that are short-lived, and these aren't necessarily virtual. So a virtual particle really appears and disappears without affecting the overall status of things. It borrows energy, it's created, it goes away, it gives back the energy. Now, the particles that disappear immediately in colliders usually decay into other things. For an example, you can have a muon, which is a charged particle that can very quickly decay into other particles, an electron, tau, into muon neutrinos. You can have particles that are very short-lived. The ones that we've looked for at colliders, not necessarily particles, but things where you have multiple quarks coming together. So quarks are one of the basic building blocks of the standard model, so of normal matter. You put three quarks together, you get things like protons or neutrons. 2 ups, 1 down, you get a proton. 2 downs, 1 up, you get a neutron. 3 is a stable configuration, but people have also found things like tetraquarks, pentaquarks, or even 6 quarks, hexaquarks, yes. These are ones that are short-lived because they immediately decay into something else. So this is not virtual. There's a difference here. Virtual is something that basically never really exists. It's just our way of understanding how an interaction took place. Whereas a short-lived particle at a collider is something that is not stable, so it decays into a lower energetic state. Hope that answers that question. A primordial black hole with the mass of the moon would be like 2 millimeters. Yes, I think radius diameter, is a factor 2. It doesn't matter. But yes, if you take the moon, you turn it into a black hole. Any black hole, primordial or not, if you take the moon, turn it into a black hole, it's going to be about 2 millimeters. The owl, the obscenely large. What's the owl? The obscenely something? I'm not sure what the owl is. I've heard that acronym now and I can't remember what it is. The overwhelmingly large telescope, maybe? Oh God, do we actually have an overwhelmingly large telescope? Would not surprise me. Yeah, would absolutely not surprise me. There's even going to build the even larger large telescope. Yes, overwhelmingly large telescope. Oh yeah, I can't believe they've actually done that. Not surprising, but yeah, the overwhelmingly large telescope. Yes. Anyway, there was a fun question that I wanted to get to, and then in the last 5 minutes, I'm actually going to talk about something that I prepared to talk about today. But there was a question by James that I really like of what would you say is the weakest link in cosmology's explanation of the universe? Well, we don't know what dark matter is. We don't know what dark energy is. If we go back to my nice pie chart here that I spent way too long making, by the way, you'll see that, 5% of it is normal matter, and then there's 95% of it that we don't know about. We have ideas, we have guesses, but we don't know the nature of dark matter. We don't know the nature of dark energy. We don't know how galaxies are formed around supermassive black holes. We know how galaxies are formed, but the interplay between galaxies and supermassive black holes is a bit sketchy. But what is the weakest link in the history of the universe in terms of our understanding and knowledge? I would have to say the Dark Ages. So again, if we look at the history of the universe, we have Big Bang, we have inflation, Depends where you place Big Bang. It's either before or after inflation. We've debated this before. Nucleosynthesis, you form particles, CMB. And then you have this whole period known as the Dark Ages. Now, the Dark Ages is a whole part that we just can't have access to. In between the time the CMB is formed and the first galaxy is turned on, there's nothing, no light that we can see, which means whatever happened in this phase, we can't directly see. Of course, we have bookends. We have the CMB. We have the galaxies we observe today. We can kind of interpolate between these two. But there is this big chunk of the history of the universe known as the Dark Ages, precisely because we cannot see them. This doesn't necessarily mean it's the weakest link. It's just something that is badly observed, just because we cannot observe it. But there are telescopes that are hoping to, radio telescopes that are hoping to listen to specific frequencies in the radio range of the electromagnetic spectrum that could shed light on the Dark Ages, which is really cool. So if your question about weakest link is, yeah, the Dark Ages is where the space dragons were made. So if your question is what is the weakest link in terms of our understanding, I would say either the Dark Ages or the first few seconds of the universe, which we're working on, both of these. Now, if it's in terms of what is the weakest link as for our standard model of cosmology, well, there are some issues we need to address, like why does the expansion rate of the universe look differently depending on who we ask? And, what is going on with the way structures form? Maybe we found galaxies that are too big. But I think some of the biggest questions and the most pressing questions are the nature of dark energy and the nature of dark matter. I say I'm a cosmologist, I study the universe, and then say there's 95% of the universe that we know pretty much nothing about. And I agree with Scott's comment here that the names of these telescopes are ridiculous, but at least they're not named after people. I absolutely agree. Please stop naming telescopes after people. People do not deserve telescopes named after them. We should not name scientific experiments after individual people, and we definitely shouldn't name scientific experiments like the JWST after a known homophobe who was a problematic person and not welcoming to people in the queer community like myself. We should absolutely not be naming telescopes after people, and not after administrators who did not much. Anyway, ranting aside, yes, telescope names are ridiculous, but I'd much rather have the overwhelmingly large telescope than something named after a very problematic person. Hopefully JWST can pierce the Dark Ages, hopefully. There's a lot of cool ideas there. But yeah, some of the biggest open questions are what is dark matter, what is dark energy? On that note, we talked a bit today about black holes. I've thrown out comments about rotating black holes. We've talked about dark energy. What is dark energy? There were some questions about the expansion of the universe and how dark energy plays a role with this, and how dark energy changes with the expansion of the universe. So, a couple weeks ago, there was a paper with very provocative paper that skipped the preprint stage, went straight to publication, big press release. So many unknowns in today's discussion. Cosmology seems to be a safe job, that an elevator escalator repair jobs. That's a very odd thing to put together. Like, I don't want to think about elevators breaking down, thank you. But yes, it's a lot of unknowns in cosmology. There was a paper a couple of weeks ago with the very provocative conclusion, and the press releases, so you've probably heard about it in the news. Scientists claim that supermassive black holes are made of dark energy, or are creating the dark energy that is causing the accelerated expansion of the universe. Let's recap. Supermassive black holes, big, huge, massive objects at the center of every galaxy. Big gravitational objects pulling things together, behaving very much like a gravitational object pulling things inwards. Dark energy pushing the universe outwards, accelerated expansion, behaving very much like something with negative pressure, kind of like an anti-gravity pushing things outwards. So come along with this idea that the supermassive black holes are producing dark energy, and the response in the community was kind of like, what? So big claims require big proof. And if you're going to make a claim that supermassive black holes are producing dark energy, this requires considerable proof. So let's backtrack. What is going on here? So we know that black holes are a thing. they are a solution. Mathematically, black holes are a solution to Einstein's equations. So Einstein's equations tell you how things behave in general relativity. Black holes are a solution. But there are two different solutions that you can think. There are multiple solutions to the Einstein equations, but not too many. We've only found like a handful of solutions. We can use these both in terms of describing the universe itself and the objects within the universe in terms of like gravitational objects like black holes. In terms of black holes, you can find two stable solutions. You can find the rotating ones and the non-rotating ones. The non-rotating ones are called Schwarzschild black holes. They're they're a lot simpler than rotating ones. So we normally work with Schwarzschild black holes, even though we know realistically all black holes are actually rotating, which makes them Kerr black holes. Kerr black holes are another solution to the Einstein equations. So we have two solutions already. We have Kerr black holes rotating and Schwarzschild black holes non-rotating. But Kerr black holes are difficult to work with, so we usually ignore that. And then when we talk about the metric of the universe, we have what is known as a de Sitter universe, which is a universe expanding with a cosmological constant. We have what is known as a Friedmann-Robertson-Walker-Lemaitre metric, which is the expanding universe, a flat expanding universe that appears to match our description. And here's the thing, you can put some of these together, but not all of them. So if you take a simplified approach about the expansion rate of the universe, you can use Kerr black holes or Schwarzschild black holes. But if you take the realistic description of the expansion rate of the universe, like how the space-time itself behaves, this is the FLRW metric, Friedmann-Lemaitre-Robertson-Walker metric, and this, we don't know how to put Kerr black holes into it. So when we're talking about black holes within the universe, and we want to consider the whole system of a black hole and the expanding universe, we either simplify our equations about the expansion of the universe, or we simplify our equations about black holes. If we use rotating black holes, we don't know how to put a rotating black hole within an expanding universe like the one we've observed. We just don't know how to. This is where we use numerical tricks to get around this. We use approximations. Now, the expansion of the universe we know is currently being driven by dark energy. Now, as to what is dark energy, we don't know. And there have been a lot of questions of, could dark energy be the result of a back reaction, going back to how Scott phrased the comment before about the universe reacting with itself. So if you have a lot of objects in the universe, as the universe grows, these are going to grow as well. And this can kind of have a reaction where it propels itself forward. So you could have a back reaction where the objects in the universe are kind of giving off a negative binding energy. So as they come together, they have a binding energy, which could then go out into the universe and affect the way the expansion of the universe is behaving. However, if you take everything that we know of in the universe and put it together and try to calculate the back reactions, you cannot explain the accelerated expansion of the universe. It's not enough. It's only a small amount. Now, we know that supermassive black holes are part of this 5% of normal matter. Scott's question was a plan to bring up this topic. Absolutely. I've kind of been guiding, despite the randomness of the conversation, I've actually been guiding us towards this point with some things I've already talked about. At least that was the intention, kind of foreshadowing. So, supermassive black holes are massive, mysterious objects at the center of every galaxy, but they are still part of this 5% of normal matter. Okay, so if I go back to the nice pie chart that we have here, supermassive black holes are within this 5% at the top. So if we count all of them, and they're like 0.05% of this 5%, so they're a very, very, very small contribution. Which is why, when we've always asked this question of, do we need to consider the back reaction between objects and the universe? The answer is usually no, because we've tried and it's a very small effect. But then you can ask the question of, do we need to consider the back reaction of a rotating black hole in an expanding universe? And the answer here is, we have no idea how to answer this question mathematically, but probably not, because we expect it to be a very, 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 very small effect. I will take care of myself, and I'll do my best to take care of the CMB. Thanks for stopping by, David. Great to see you. Have a great evening. Diana using secret mind control powers to make us ask the questions needed. Yes. No, you will just ask questions that allow me to perfectly guide us to what I wanted to talk about today, which is very convenient. So, do we need to care about supermassive black holes affecting the expansion rate of the universe? Well, most people have said, well, we have no idea how to answer this question mathematically, but based on everything we know, probably not. Because it would be a small effect, and we don't know how to calculate it, but it's a small effect, so let's ignore it. So what this team of people have done recently is say, what if we actually do need to consider the effect or the coupling between the expansion rate of the universe and black holes, supermassive black holes? So they asked themselves, what if we do need to consider this, and how big would this effect be? And can it be enough to explain dark energy? So then they set out with the idea of, let's assume that it is enough to explain things and see what happens. Or let's assume that this binding energy, this negative binding energy of the supermassive black holes could drive the accelerated expansion of the universe. What this would mean is that these supermassive black holes would grow in the same way the expansion rate of the universe is growing. As the universe expands, these supermassive black holes would also expand. They would become a lot more massive. I'm losing my voice. So if supermassive black holes are coupled, are tied to the expansion rate of the universe, as the universe expands, these supermassive black holes should expand as well. Caveat here, supermassive black holes are already expanding and growing because they're in galaxies and they're accreting matter. So what this team did is they looked for galaxies where there's not much matter that can fall into the supermassive black holes. And then they took a snapshot of these and asked the question of, based on, so at different time points. So they took young galaxies and old galaxies, but only one sample of each galaxy because we cannot watch one galaxy evolving in time. But yeah, gravitational bound objects would not expand as the universe expands unless there is this back reaction effect where the objects expanding is what's creating the expansion of the universe with the negative binding energy. So usually, yes, gravitationally bound objects do not expand as the universe expands. But here we're asking the question of, what if they do? What if the supermassive black holes do? Would this be enough to explain dark energy? So they looked for a bunch of galaxies where they don't expect the supermassive black holes to be growing much. They took a bunch of old galaxies, middle-aged galaxies, young galaxies, and in these, they asked if there is a standard picture that ties together all of these items, would this explain dark energy? And the answer they found is yes. So, based on the galaxies, the snapshots of the galaxies they looked at, they actually found that the supermassive black holes of these galaxies appear to grow at a rate that is compatible with driving the accelerated expansion of the universe. So from here, they reached the conclusion of these supermassive black holes are driving the expansion rate of the universe. Are you convinced? There are a lot of open questions here, a lot of ifs, a lot of maybes, a lot of potentials. First of all, they're assuming that these supermassive black holes are only growing because of this coupling to the expansion rate of the universe, and there is nothing else falling on these supermassive black holes. Another big assumption they've made is that there exists a universal law tying together the size of a supermassive black hole and the size of the galaxy around it. This is not something that we have any reason to assume to be true. They also assume that this coupling exists and do their whole experiment assuming that the coupling exists and then look for it. Whereas the default would be to assume that it doesn't exist and then look for it. But if you already implicitly assume this, you're more likely to get that answer out. And they are, again, so they are trying to embed rotating black holes in the expansion rate of the universe using something that we're not sure if it's valid, which is this coupling between the two things. And then they reach this dramatic conclusion. As Scott is saying, correlation does not imply causation here. So you would think the supermassive black holes would have to be uniformly distributed in space to make this work. Excellent point, Paul, and this is also a point that other people have mentioned. So just from a physical perspective, if we think about it, supermassive black holes are centered in galaxies. whereas we know that the universe is expanding everywhere equally. If this claim is true, it's saying that the effects of dark energy should be more dominant where there are these supermassive black holes. Of course, this then spreads out, but it's also saying that something that is part of this 5% of normal matter is accounting for the effects of this 69% of dark energy. So when this paper came out, the general response in the scientific community was, I'm skeptical. And a lot of people were very vocal about this on Twitter, like, I'm very skeptical. Apparently, there was a whole debate in my research group and everyone was skeptical. I missed that because I was traveling at the time. So we are still live, yes, going on for a bit longer today. So this is a big claim, you know. Supermassive black holes are dark energy. This is a massive claim. There was a press release. There was a lot of noise about it. But big claims require big evidence, and they don't have that. So this is a very interesting thing to study, and people should absolutely be looking at this question of, do we need to consider any effects of supermassive black holes on the expansion rate of the universe? This is absolutely something worth doing. But I am highly skeptical about their claim being true. If I was a betting, so they say that they have 3.6 sigma, which means the chances of this not being the case are like 0.02%. As if I were a betting person, I would bet against this model. And I think most people in the scientific community would not bet for this model to be true. So there will probably use words stronger than skeptical. Yes, there have been very many not polite replies to this, especially on Twitter, where people just like being nasty. But yeah, it's very interesting. But it's not something like, it's something that is a starting point and not something that you claim this is, you know, this is where we are. So there was a press release, there was a lot of news about it. I know a few of you have asked me over the last few weeks, and I've been vague about my answer because I wanted to read up more about it today, and today I read the paper. The good thing about waiting about a month is since then there have already been a couple of papers proving this one wrong, like, no, it doesn't work because, no, it doesn't work because here's some math, no, it doesn't work because here's some assumptions you missed. So it is a very interesting idea, but I don't think we're at the stage yet where we can make this absolute claim. So do supermassive black holes produce dark energy? Probably not, is the current prevailing opinion, but it's interesting. And the fact that these supermassive black holes are growing in an unexpected way is by itself very, very, very interesting. And we should figure out what these supermassive black holes are doing, because it might help us understand the origin of these supermassive black holes. But from there to go to dark energy is a bit of a jump. So we already talked about this a bit in the stream, about rotating black holes, about dark matter, about dark energy, about back reactions, and then hopefully I set enough seeds that tying it together made sense. Does this affect the dark matter percentage as well somehow? No, this is just connecting supermassive black holes to dark energy. Dark matter does not appear in this. Do we know the source of the correlation, or is it just... We don't know yet, so there's several questions here. Is there really a correlation? If there is a correlation, what is causing it? What is the source of this correlation? And does this actually support the conclusion that the authors reached? There's a lot of open questions, but in general, the reaction in the community was, yeah, no. So, as always, if you see a big claim like this in popular science, be skeptical. You know, go into things with a good amount of skepticism, because if there was something big and dramatic like this, the scientific community would be buzzing with it. And usually it's a good, of course, we're always going to be skeptical with big claims, but if there is big evidence to support big claims, we'll be buzzing with it. If you see that a lot of people in the community are like, let me sit this one out, there's probably a reason for it. So it is a very interesting area of research. It's a good question to ask, but I don't think we can say that this is the answer. So we still don't know what dark energy is. I personally do not think it's going to be supermassive black holes, but maybe in the future we'll find a lot more evidence that will point in this direction. But currently we're not at the stage to make this claim just yet. So after a few weeks, I finally answered the question. When this paper came out, I was on holiday and I was like, well, there's a task for future Cup of Cosmology episode. So, but it's always good to revisit these popular science news because it's a very interesting one to talk about. So, an hour and 10 minutes into the stream today, we had a lot of really fun questions. It took me quite a while to go through the questions, also a lot of tangents. You got me talking about maps, about daylight saving time, always a good thing to make me rant about. But we've had a lot of cool topics. Gravitation, we didn't have gravitational waves today, sorry. CMB, dark matter candidates, supermassive black holes, dark energy, tying everything together, rotating versus non-rotating black holes. I have a note to read up about charged black holes properly and maybe answer that at some point soon. But hopefully I've been able to answer some of your questions today, and we went off tangent a few times, but that's always fun. So thank you everyone for joining. This has been great fun. We've had some really, really, really cool questions today, some really cool topics. Cup of Cosmology should be back online next Sunday, same time as today. That's 7 p.m. Central European time, 2 p.m. if you're on the East Coast, 11 a.m. if you're on the West Coast in the US, because we have not yet done the stupid thing of changing our clocks. So next weekend, there will also be 1 hour difference if you're used to the usual time slot. Do you have any follow-up on my 2D time Nerds Night from a few streams ago? Right, if there's 2 dimensions of time. I do not. I got very distracted. I do remember the question, 2 dimensions of time. I will ask that around the office and see what people think about that. When does our clock change? 2 weeks from now. It's always the last Sunday in March for us. So 2 weeks from now. Yes, please do. If you haven't done so already, subscribe, like the video, leave a comment. Everything does help. So please do boost engagement. And I know a couple of you promote me on Twitter and on other social media, and I really appreciate it. You know, every week I just write a really bland thing on Twitter for like Cup of Cosmology tomorrow. And then there's people like Paul hyping it up with all your questions about the universe. I need to hire you all as my PR agents because, yes. Go ahead and ask about 3D time as well. I'll add it to the list. Multiple dimensions of time. Let's just say n dimensions of time and see what happens. Thank you everyone for being here. Thank you to everyone who's followed the show, who helps promote the show. Are you going 1 hour ahead or behind? Next week is same time as today, and then the week after will be clocks go forward. It's spring, clocks go forward, so then everything's an hour later. Makes no sense. Okay, or an hour earlier, depends on your... Time is relative. Time is messy. There is always a time zone converter on cupofcosmology.com that I update on the day we change the clocks. Every 6 months, I remember to update it. So if at any point you don't know when the next stream is, you can go to cupofcosmology.com, scroll down, click on time zone converter, and you'll get the time of the next stream in your own time zone. It's set up to match your time zone to mine. So you can always check it out there. Okay. Try this again. I feel like this is Lord of the Rings now. I keep saying goodbye and then another question, another comment, and 3 hours later we'll still be here. Okay, so I need to watch those again. Thank you everyone for joining. This has been great fun. Cup of Cosmology will be online next Sunday, same time as today. And as always, if you have more questions, you can reach out to me on Twitter, on Mastodon, or on contact@cupofcosmology.com. I'm slow replying to emails. I'm quicker replying to messages on Mastodon. Twitter messages is once every week when I open Twitter. So the easiest way to contact me is contact@cupofcosmology.com or on Twitter or on Mastodon. Twitter is DCHooper91 and my Mastodon is pinned on my Twitter. So you can find me there. I hope to see you all next week, same time as usual, and I hope in the meantime you'll stay safe and take care of each other.